The Milky Way Galaxy is a colossal barred spiral galaxy, a vast rotating disk of stars, planets, gas, dust, and dark matter stretching about 100,000 light-years across. It contains hundreds of billions of stars and possibly trillions of planets, all bound together by gravity in a magnificent cosmic dance. Its spiral arms wind outward from a bright central bar, where countless suns cluster densely near the core. Most of its mass, however, is invisible, composed of dark matter, the mysterious substance that holds the galaxy together as it spins. The Milky Way is not static. It breathes and evolves, birthing new stars from interstellar clouds, even as old ones fade into white dwarfs, neutron stars, or black holes. And today, we're going to take a journey around this incredible galaxy we call home. So, watch this video till the end and subscribe to the channel. Let's begin. As we drift inward from the vast reaches of the Milky Way's spiral arms, we find our own humble home, the solar system, quietly orbiting within one of the galaxy's lesser-known branches. This region is called the Orion Arm, or more precisely, the Orion Spur, a small partial arm nestled between two of the Milky Way's major spiral structures, the Perseus Arm and the Sagittarius Arm. Here, about 26,000 light-years from the galactic center, the Sun and its family of planets journey through space at a breathtaking 828,000 kilometers per hour, completing one full orbit around the galaxy roughly every 230 million years. A galactic year. Our corner of the galaxy is relatively peaceful, a cosmic suburb far from the chaos of the crowded central bulge and the violent births and deaths of massive stars closer to the core. Yet, it is far from empty. The Orion Arm is dotted with some of the most stunning celestial landmarks known to humanity. The Orion Nebula, a stellar nursery glowing with newborn stars. The Pleiades Cluster, a gathering of brilliant young suns, and the Horsehead Nebula, sculpted by interstellar winds and radiation. These regions remind us that our galaxy is still alive with creation, even in its quieter neighborhoods. From our vantage point on Earth, the Milky Way appears as a glowing band stretching across the night sky, because we are observing the dense plane of the galactic disk from within it. Dust clouds block much of our view toward the center, making our local environment seem isolated. Yet in reality, we are part of an immense, interconnected galactic web. Every twinkling star you see on a clear night, from the familiar constellations of Orion and Scorpius to the distant faint specks, is a neighbor within this same galactic arm, sharing our slow but steady orbit through the stars. It's humbling to realize that our entire solar system, every planet, moon, and comet, is just one of countless systems scattered through this vast spiral. Yet, it is from this small, stable corner of the galaxy that life has emerged, consciousness has awakened, and humanity has begun to look outward, seeking to understand the immense cosmic ocean we inhabit. As we leave the familiar comfort of our solar neighborhood and look at the Milky Way on a grander scale, its structure reveals itself as a masterpiece of cosmic architecture, vast, layered, and beautifully intricate. The galaxy is not a random scattering of stars, but a precisely balanced system with distinct regions, each playing a unique role in its overall form and evolution. The Milky Way is composed primarily of four major components: the galactic disk, the central bulge, the halo, and its magnificent spiral arms that sweep gracefully through space like celestial ribbons. At the heart of the Milky Way lies the galactic bulge, a densely packed, spheroidal region filled with billions of ancient stars, orbiting in complex, overlapping paths. This golden hub glows with the warm light of old, metal-rich suns that formed in the early epochs of the galaxy's history. The bulge also harbors the galaxy's most mysterious and powerful resident, Sagittarius A, a supermassive black hole with a mass of about 4 million suns. Around it, stars orbit at breathtaking speeds, some whipping around in mere decades, a testament to the unimaginable gravitational forces concentrated there. Surrounding the bulge is the galactic disk, a sprawling, flattened structure about 100,000 light-years wide and roughly 1,000 light-years thick. This disk is the galaxy's bustling metropolis, the region where most of the Milky Way's stars, gas and dust reside. Here, clouds of interstellar gas serve as the raw material for new stars, while older stars glide serenely through lanes of starlight and shadow. The disk is also where we find the spiral arms, the Milky Way's most iconic features. These arms are not solid structures, but rather density waves, where material bunches together as it orbits the galaxy, triggering bursts of star formation. Young, hot, blue stars and glowing nebulae trace out these arms, giving the Milky Way its stunning, swirling appearance. Encasing all of this is the galactic halo, an enormous, nearly spherical region that extends far beyond the visible disk. The halo contains ancient, metal-poor stars and mysterious globular clusters, tightly bound groups of old stars that date back to the earliest days of the galaxy's formation. But perhaps most importantly, the halo is dominated by dark matter, the invisible substance that accounts for most of the Milky Way's mass. It forms a vast, unseen cocoon that keeps the galaxy gravitationally stable, preventing it from flying apart as it spins. Together, these regions form a system of balance, a living galaxy where stars are born, evolve, and die in a continuous cycle that has persisted for billions of years. The Milky Way's structure is a story written in starlight and shadow, a dynamic interplay between chaos and order, between gravity and motion, shaping the cosmic home we call our own. At the very heart of the Milky Way lies a region unlike any other, a place where gravity bends light, time slows, and matter itself teeters on the edge of oblivion. This is the galactic center, an extraordinary cosmic environment that serves as the beating heart of our galaxy. Hidden behind dense clouds of interstellar dust, invisible to ordinary telescopes, it radiates fiercely in radio, infrared, and X-ray wavelengths, revealing a turbulent and energetic domain governed by a single, overwhelming presence: the supermassive black hole, Sagittarius A. Sagittarius A sits at the very center of the Milky Way, about 26,000 light-years from Earth, with a mass equivalent to 4 million suns compressed into a region smaller than our solar system. Its gravitational influence is so immense that it dictates the motion of everything in its vicinity: stars, gas, and even light itself. Astronomers have tracked individual stars, such as the famous S2, orbiting this invisible giant at incredible speeds, some reaching over 11,000 kilometers per second, completing their dizzying loops in just over 16 years. These stellar dances provide direct evidence that an object of unimaginable density lurks at the galaxy's core. The environment around Sagittarius A is one of extremes. The gravitational forces near the event horizon, the boundary beyond which nothing can escape, are so powerful that they warp space-time itself. Streams of gas spiral inward, heating up to millions of degrees and emitting intense X-rays before vanishing into the black hole's darkness. Occasionally, Sagittarius A flares brightly, unleashing bursts of high-energy radiation that ripple across the surrounding region, a faint echo of its hidden, devouring power. But the galactic center is more than just a black hole. It is a crowded, chaotic hub filled with dense star clusters, supernova remnants, and massive molecular clouds, all jostling under the immense gravitational pull of the core. Some of the most massive stars in the galaxy live here, shining brilliantly for brief cosmic moments before exploding as supernovae, seeding the area with heavy elements. Magnetic fields twist and dance across the region, channeling energy in ways scientists are only beginning to understand. Despite its violence, this central region plays a crucial role in the Milky Way's evolution. The black hole acts as both a destroyer and a regulator, swallowing matter, but also shaping the galaxy's structure through its gravitational influence. It may even help govern star formation rates in the surrounding bulge, subtly balancing creation and destruction on a galactic scale. Through advanced observatories like the Event Horizon Telescope, humanity has begun to peer directly into this mysterious realm, even capturing the first image of Sagittarius A in 2022, a glowing ring of light encircling a shadow, marking the threshold of the unknowable. The galactic center reminds us that the Milky Way, for all its elegance and order, is built around a heart of darkness, a gravitational engine driving the cosmic symphony that sustains our galaxy. When we look across the vast expanse of the Milky Way, we find that not all stars are created equal. Like people, stars are born, live, and die. And across the galaxy, we can see them at every stage of that cosmic life cycle. This diversity gives rise to what astronomers call stellar populations, a way to classify stars based on their age, composition, and location within the galaxy. From the glittering blue giants of the spiral arms to the ancient red elders of the halo and bulge, each region of the Milky Way tells a different chapter of the galaxy's ongoing story. The spiral arms, those luminous bands that wind outward from the galactic center, are the bustling nurseries of star formation. Here, dense clouds of gas and dust continually collapse under gravity to give birth to young, hot, blue stars. These massive stars burn intensely, shining with fierce luminosity, but living only a few million years before dying in spectacular supernova explosions. The Orion Arm, where our Sun resides, contains many such regions, including the Orion Nebula and the Eagle Nebula, where brilliant new stars illuminate the interstellar clouds around them. These youthful, energetic populations make the spiral arms sparkle and define the very structure of the galaxy when viewed from afar. In contrast, the galactic bulge at the center and the halo surrounding the disk are the realms of the old and the enduring. The stars found here are typically ancient red giants and metal-poor stars, relics of the Milky Way's earliest generations. The bulge is dense with older, evolved stars that have exhausted most of their hydrogen fuel, glowing with a soft reddish hue. In the halo, far above and below the galactic plane, stars are sparse but ancient, some dating back over 12 billion years, formed when the galaxy itself was still taking shape. These are known as population 2 stars, composed mostly of hydrogen and helium, with only trace amounts of heavier elements produced by earlier supernovae. Meanwhile, stars like our Sun belong to the galaxy's population 1. Younger stars enriched with heavier elements such as carbon, oxygen, and iron, forged in the cores of previous generations. These metals are crucial for the formation of planets and ultimately for life as we know it. In this sense, the distribution of stars across the galaxy is also a map of cosmic evolution. The farther from the spiral arms and deeper into the halo you go, the older and more primitive the stars become. Together, these stellar populations paint a picture of a galaxy that is constantly evolving, a living system where birth and decay are in perfect harmony. The blazing blue giants of the arms represent the galaxy's youth and energy, while the ancient red stars of the bulge and halo are its memory, the cosmic elders that have witnessed billions of years of galactic history. And somewhere in between, orbiting a modest star in a quiet arm, humanity watches the dance unfold, a small flicker of awareness in a galaxy filled with light. From the brilliant young stars of the spiral arms, our journey naturally leads us to the places where those very stars are born, the stellar nurseries of the Milky Way. These vast, cold clouds of gas and dust are the wombs of the cosmos, where gravity, time, and energy collaborate to forge the fiery hearts of new suns. Known as star formation regions or nebulae, these pockets of interstellar material are scattered throughout the galaxy's spiral arms, marking the sites where the cycle of cosmic creation is most active. They are the luminous factories of starlight, shaping the next generation of stars, planets, and, perhaps, life itself. The process of star formation begins in immense molecular clouds, composed primarily of hydrogen gas mixed with helium and trace elements. These clouds can span hundreds of light years and contain enough mass to form thousands of stars. Normally, they remain cool and stable, drifting silently through the galaxy. But when disturbed by the shockwave of a nearby supernova, the collision of two molecular clouds, or even the gravitational pull of a passing spiral arm, parts of the cloud begin to collapse under their own gravity. As the material condenses, the center of each fragment grows hotter and denser, forming a protostar, a young embryonic star still wrapped in its dusty cocoon. One of the most famous examples of such a region is the Orion Nebula, located about 1,300 light-years from Earth in our own Orion Arm. Visible even to the naked eye as a faint patch in Orion's sword, this nebula is a stunning expanse of glowing gas and dust spanning 24 light-years across. Within it, clusters of young stars, such as the trapezium cluster, are lighting up the surrounding gas, sculpting the nebula's delicate filaments with their intense radiation and stellar winds. The Orion Nebula is a window into the galaxy's most creative workshop, where the forces of gravity and heat wrestle within the womb of interstellar space to give birth to new suns. Other spectacular stellar nurseries include the Eagle Nebula, home to the famous Pillars of Creation, towering columns of gas and dust captured by the Hubble Space Telescope. These cosmic spires stretch for light years, their tips glowing as newborn stars carve cavities through the dense clouds with streams of ultraviolet radiation. In the Carina Nebula, massive stars like Eta Carinae illuminate and agitate their surroundings, triggering new waves of star formation in a self-sustaining cycle of creation and destruction. Across the Milky Way, countless such regions exist: the Rosette Nebula, Lagoon Nebula, Westerlund II, and many more, each a living testament to the galaxy's ongoing evolution. Inside these nurseries, the conditions are both violent and nurturing. As young stars ignite, their powerful stellar winds and radiation begin to push away the leftover gas and dust, shaping the surrounding material into glowing shells and intricate filaments. Some of the expelled material may later coalesce into protoplanetary disks, where planets, moons, and asteroids take form around the newborn stars. In this way, every star-forming region is not just a birthplace for stars, but also for solar systems, potential cradles of life scattered across the galaxy. These regions also reveal the delicate balance of galactic life. The same massive stars that ignite within them eventually die in cataclysmic explosions, spreading heavy elements like carbon, oxygen, and iron back into the interstellar medium. These elements then enrich the next generation of clouds, ensuring that every new cycle of star formation is more chemically complex than the last. Thus, the galaxy is constantly renewing itself, a great self-sustaining ecosystem where death feeds birth and birth gives rise to new worlds. The beauty of these star-forming regions is not merely visual, but philosophical. They remind us that creation in the universe is not a singular event, but a continuous process, an eternal rhythm of transformation woven into the very fabric of the Milky Way. Every star that twinkles in the night sky was once part of a cold, silent cloud of gas that, through gravity and time, burst into light. The very atoms that compose our bodies, forged in the hearts of long-dead stars, may have been recycled through such nebulae countless times before, finding their way into us. From the quiet spirals of molecular gas to the radiant brilliance of newly born suns, the star-forming regions of the Milky Way embody the essence of cosmic renewal. They are the nurseries of light, the seeds of future worlds, and the evidence that even in the cold emptiness of space, creation never ceases. As we drift onward from the luminous birthplaces of stars, we inevitably arrive at the other end of the cosmic life cycle, stellar death. For every radiant sunrise in the galaxy, there must come a sunset. And in the Milky Way, these endings are as awe-inspiring as they are destructive. When stars die, they do not simply vanish. They transform, releasing their material, energy, and elements back into the galaxy. These final acts, whether quiet or cataclysmic, are what keep the Milky Way alive, seeding the cosmos with the ingredients for new stars, planets, and even life itself. A star's fate is determined by its mass. Small and medium-sized stars, like our Sun, live long, stable lives, burning hydrogen into helium in their cores for billions of years. When their fuel runs low, they swell into red giants, shedding their outer layers into space in a slow, elegant death. What remains is a white dwarf, a small, dense core roughly the size of Earth, but with the mass of the Sun. These faint, cooling embers can glow for trillions of years, slowly fading into the cosmic darkness. The shells of gas they leave behind form beautiful planetary nebulae, such as the Ring Nebula or the Helix Nebula, their colourful halos shining briefly before dispersing into interstellar space. But for massive stars, those at least 8 times the mass of the Sun or more, the end is far more dramatic. These colossal suns burn through their fuel rapidly, living for only a few million years before collapsing under their own immense gravity. When the nuclear fire in their cores goes out, the delicate balance between outward pressure and inward pull shatters. The core implodes, and the outer layers are blasted away in one of the most powerful events in the universe, a supernova explosion. In a matter of seconds, a dying star releases more energy than our Sun will emit over its entire lifetime. These explosions are both violent destroyers and cosmic creators. In the heart of a supernova, temperatures soar high enough to forge the heaviest elements: gold, silver, uranium, and more. Elements that could not have formed in ordinary stellar fusion. The shockwave from the blast races through space, enriching nearby gas clouds with these newly minted atoms. Over millions of years, those same clouds may collapse to form new stars and planets, incorporating the ashes of dead suns. In this way, every element in our bodies, every atom of iron in our blood, calcium in our bones, and carbon in our DNA, was forged in the heart of a star that lived and died billions of years ago. The stellar remnants left behind after a supernova depend once again on the mass of the progenitor star. If the collapsing core is moderately massive, it forms a neutron star, a city-sized sphere of pure nuclear matter so dense that a teaspoon of it would weigh billions of tons. Neutron stars are among the most extreme objects in existence, sometimes spinning hundreds of times per second and emitting beams of radiation as pulsars, sweeping across space like cosmic lighthouses. For the most massive stars of all, even neutron degeneracy cannot withstand gravity's relentless pull. These giants collapse completely into black holes, regions where matter is crushed into a singularity, an infinitely dense point where the known laws of physics break down. These stellar mass black holes silently roam the galaxy, invisible except when feeding on nearby material, which can create dazzling X-ray emissions. They are the ultimate endpoints of stellar evolution, the cosmic shadows left by the brightest of lights. Though death may seem final, it is in these endings that the Milky Way's vitality endures. Supernovae scatter clouds of enriched material, triggering new waves of star formation. White dwarfs drift silently, holding within them the memory of what once was. Neutron stars and black holes remain as eternal monuments to the forces that shaped the universe. Together, these remnants keep the galactic ecosystem in balance, a continuous loop of creation, destruction, and rebirth. The galaxy we see today, its glowing arms, its planets, its life, exists only because countless stars lived and died before us. In this endless cycle, there is no true death, only transformation. Every star's final flare contributes to the story of cosmic renewal, ensuring that from the ashes of one generation, another will rise, shining once more across the Milky Way. From the ashes of dying stars, the Milky Way renews itself, an endless rhythm of destruction giving rise to creation. This grand process is known as galactic recycling, the cosmic cycle through which the material from old, dying stars becomes the raw substance for new generations of stars, planets, and life. Far from being a static structure, the Milky Way is a living, evolving entity, constantly reshaping itself through this perpetual exchange of matter and energy. Every glowing nebula, every world, and even every atom within us is part of this unbroken chain of rebirth that stretches across billions of years. When a star reaches the end of its life, it releases its enriched material back into the galaxy. For smaller stars like our Sun, this happens gently. They shed their outer layers as planetary nebulae, dispersing elements such as carbon, nitrogen, and oxygen into surrounding space. Massive stars, on the other hand, die in spectacular supernova explosions, flinging heavy elements, iron, gold, silver, and even uranium, outward at tremendous speeds. These violent events stir the interstellar medium, the vast ocean of gas and dust that fills the galactic disk, blending the remnants of countless generations of stars into a single, shared reservoir of cosmic material. Over time, this material cools and gathers into molecular clouds, the same colossal structures where new stars are born. Within these clouds, gravity begins its patient work again, drawing gas and dust together until dense clumps form and collapse into protostars. Around these young stars, leftover debris spins into protoplanetary disks, the birthplaces of planets, moons, comets, and asteroids. In this way, the iron forged in a dying sun billions of years ago may one day solidify into the core of a rocky world, or the carbon expelled from a red giant may find its way into the chemistry of life. This continuous cycle connects all cosmic generations in an unbroken lineage. The interstellar medium acts as both graveyard and nursery, where the remnants of the dead become the seeds of the new. It is an ongoing, galaxy-wide exchange that ensures the Milky Way never stagnates. Instead, it evolves, each new cycle producing stars richer in heavy elements than the last. Early in the galaxy's history, the first stars were composed almost entirely of hydrogen and helium. Today, billions of years and countless supernovae later, the Milky Way's clouds are infused with complex elements that make possible the diversity of planets, minerals, and biochemistry that we see now. This recycling is not just physical, it's profoundly symbolic. It reveals that nothing in the galaxy truly ends. The elements in your bloodstream, the oxygen you breathe, the silicon in the rocks beneath your feet, all were forged in the nuclear hearts of ancient suns that died long before Earth even existed. You are, quite literally, the universe made conscious, born from the dust of forgotten stars. The poet's phrase, "We are stardust," is not metaphor, but fact, a testament to the Milky Way's eternal cycle of renewal. In this grand cosmic ecology, every death feeds a new beginning. Supernova shockwaves compress distant clouds, igniting fresh bursts of star formation. The galactic winds driven by dying stars enrich vast regions of space, ensuring that no corner of the galaxy remains untouched by the legacy of those that came before. Even the faint glow that pervades the galaxy, the diffuse light of countless stars, and the hum of interstellar energy is part of this continuous transformation. The Milky Way, then, is not merely a static collection of stars, but a cosmic organism, breathing and evolving over billions of years. Its lungs are the supernovae that exhale life's ingredients. Its veins, the spiral arms through which matter and energy flow. Its heartbeat, the slow but ceaseless rhythm of birth and decay. Galactic recycling ensures that creation and destruction are not opposites, but partners, two halves of the same eternal process. And so, as we look up into the night sky, what we see is not a frozen moment in time, but a snapshot of this endless cycle, a galaxy alive with transformation. Every spark of light, every dark cloud, and every planet orbiting its sun is part of a cosmic legacy billions of years old. In the Milky Way, nothing is ever truly lost. It is merely reborn in another form, shining once more as part of the galaxy's timeless story of renewal. As we continue our journey through the Milky Way, the stillness of the night sky begins to fade into motion. What appears to us as a serene canopy of stars is, in truth, an immense and ceaseless cosmic rotation. The entire Milky Way Galaxy, this sprawling disk of stars, gas, dust, and dark matter, is spinning, turning majestically around its core in a vast, gravitational dance that has persisted for billions of years. Every star, every cloud, every world within it is part of this colossal motion, including our own sun, which orbits the galactic center like a tiny ember caught in the whirl of a cosmic storm. The Milky Way's rotation is both graceful and staggering in scale. Our solar system, located about 26,000 light-years from the galactic center, travels around the galaxy at an astonishing speed of nearly 828,000 kilometers per hour, or about 230 kilometers per second. Even at such blistering velocity, one complete orbit takes roughly 230 million years, a period known as a galactic year. That means, since the Sun was born about 4.6 billion years ago, it has circled the Milky Way's core only about 20 times. The sheer size of the galaxy makes its motion imperceptible to us on human timescales. Yet, across cosmic ages, everything within it traces grand, sweeping arcs through space. This vast rotation is governed by gravity, the invisible force sculpting the structure of the galaxy. Each star, from the massive blue giants in the spiral arms to the faint red dwarfs of the outer regions, moves under the combined gravitational influence of all other stars, gas clouds, and, most mysteriously, dark matter. The Milky Way does not spin like a solid object. Instead, different parts of it rotate at different speeds. The stars closer to the center orbit faster, while those farther out move more slowly. However, when astronomers began measuring the actual speeds of stars and gas in the galaxy, they found something startling. The outer stars were moving much faster than they should be based on the visible mass alone. This puzzling observation led to one of the greatest scientific mysteries of all time, the discovery of dark matter. If the galaxy were made only of the matter we can see, stars, planets, and gas, its outer regions should rotate more slowly, and the gravitational pull of the core would not be strong enough to keep them bound. Yet, the outer stars continue to move at high velocities, refusing to scatter into space. The only explanation is that the Milky Way contains vast amounts of invisible mass, dark matter, forming a massive halo that envelopes the entire galaxy and holds it together. Though dark matter cannot be seen or directly detected, its gravitational effects are undeniable. It acts as the galaxy's cosmic glue, keeping stars in their orbits and maintaining the spiral structure. Without it, the Milky Way's rotation would tear it apart. Current models suggest that dark matter makes up about 85% of the galaxy's total mass, while all the visible stars, gas, planets, and dust account for less than 15%. In a profound sense, most of the Milky Way, most of the universe itself, is made of something we cannot yet see or fully understand. The galaxy's rotation is not limited to its stars. Its interstellar gas and dust also follow the galactic flow, swirling through the spiral arms in rhythmic waves. These arms are not rigid structures, but rather density waves, regions where material temporarily bunches up, triggering the formation of new stars before drifting onward. It's as though the galaxy's rotation continuously sculpts its own beauty, creating luminous patterns that shimmer through the dark. The entire Milky Way, in this way, behaves like a vast, rotating disk of life and motion, a cosmic whirlpool driven by gravity and balanced by unseen matter. Even the central bar and bulge rotate, though more slowly and chaotically than the disk. The stars in the bulge move in intricate, overlapping orbits, influenced by the gravitational pull of the supermassive black hole, Sagittarius A, and the dense star clusters surrounding it. This complex rotation fuels the flow of gas toward the core, sometimes igniting bursts of star formation or feeding the black hole itself. It's a delicate, self-regulating system that has persisted for eons, a cosmic equilibrium between gravity's pull and motion's inertia. For humanity, understanding galactic rotation is more than an astronomical curiosity. It's a window into the hidden structure of the universe. It shows us that the cosmos is not static, but alive with motion, governed by laws that apply from the scale of atoms to the scale of galaxies. It also reveals how little we truly know. Dark matter remains one of science's most profound enigmas, silently shaping not only the Milky Way, but every galaxy in the universe. When we look up at the stars, we are not simply staring into a fixed sky. We are watching, though too slowly to perceive, the spinning grandeur of a galaxy in motion. The sun, the earth, every distant star you see, all are carried together on an endless voyage around an invisible center. The Milky Way's rotation binds us in a cosmic rhythm, connecting every world, every star, and every atom in a shared motion that began long before us and will continue long after we are gone. The next time you gaze at the night sky, remember that you are part of this magnificent rotation, a traveler aboard a planet, spinning within a solar system, orbiting within a galaxy, all turning together in a silent, eternal dance. The Milky Way is not merely our home, it is our motion, our history, and our destiny, bound forever to the mysterious forces that make the universe turn. As we drift outward from the luminous disk of the Milky Way, beyond the glittering spiral arms and into the silent outskirts, we enter one of the most mysterious and least understood regions of our galaxy, the galactic halo. It is here, in this vast, nearly invisible expanse, that we encounter the profound enigma that holds the galaxy together: dark matter. Though unseen, this elusive substance forms the Milky Way's invisible skeleton, providing the gravitational glue that keeps everything bound in its graceful rotation. Without it, our galaxy, and indeed the universe itself, could not exist in the form we know. The galactic halo is a vast, spherical region extending far beyond the visible disk, possibly reaching out to 300,000 light-years or more from the galactic center. It is faint and diffuse, home to some of the oldest and most ancient stars in existence. These stars, often gathered in dense globular clusters, orbit the galaxy in long, elliptical paths, like ancient sentinels circling the heart of the Milky Way. But these visible stars make up only a tiny fraction of the halo's true mass. Most of it, about 85%, is composed of dark matter, a substance so mysterious that it neither emits, reflects, nor absorbs light. It is utterly invisible, detectable only through its gravitational influence on the things we can see. The existence of dark matter first became evident when astronomers studied the rotation curves of galaxies. According to the laws of physics, stars farther from the galactic center should orbit more slowly, since the visible mass decreases with distance. But observations revealed the opposite. The outer stars were moving far faster than expected. This could only mean one thing: there was additional, unseen mass extending far beyond the visible edge of the galaxy, exerting enough gravity to keep those stars in motion. That mass is what we call dark matter, and it surrounds the Milky Way like an invisible cocoon. To imagine it, picture the glowing disk of the Milky Way as a thin, radiant whirlpool suspended inside a massive, transparent sphere. The luminous stars, nebulae, and gas clouds that we see make up only a small portion of this grand structure, while the halo of dark matter envelops it, unseen but immense. It is this halo that stabilizes the galaxy's rotation, anchoring the spiral arms and preventing the disk from unraveling under its own centrifugal force. The Milky Way, in essence, is a galaxy of light bound by darkness. The nature of dark matter remains one of science's greatest mysteries. It is not made of ordinary atoms, and it does not interact with light or electromagnetic forces. The leading theories suggest that it could be composed of exotic, yet undetected particles such as WIMPs, weakly interacting massive particles, or axions. Other ideas propose that dark matter could consist of massive compact halo objects, or MACHOS. Things like black holes, neutron stars, or brown dwarfs hidden within the galactic halo. Yet, despite decades of searching with the most advanced detectors and telescopes, dark matter continues to elude direct observation. Its existence is inferred solely through the dance of the stars and galaxies that move to its gravitational tune. Even though we cannot see it, the effects of dark matter are everywhere. It not only holds galaxies together, but also shaped the large-scale structure of the universe itself. After the Big Bang, dark matter acted as a cosmic scaffold, drawing in ordinary matter through gravity and allowing galaxies like the Milky Way to form and cluster together. Without dark matter's stabilizing presence, the universe might have remained a thin, diffuse mist of gas and radiation, never condensing into stars, planets, or life. In the Milky Way, dark matter defines the boundaries of our galactic home. The halo extends far beyond the visible disk, influencing not just the motion of stars, but even the paths of satellite galaxies, such as the Large and Small Magellanic Clouds, which orbit within its gravitational reach. It is an enormous, unseen domain, a quiet ocean of mass enveloping the familiar brilliance of the galactic core and arms. The visible stars of the Milky Way, those bright beacons that fill our night sky, represent only the tip of an immense cosmic iceberg. For every atom of ordinary matter, there are roughly 5 atoms worth of dark matter silently shaping the universe around it. In this way, the story of the Milky Way is also the story of the unseen, of the forces that work in silence to sustain creation. As humanity peers deeper into the cosmos, the study of dark matter stands at the frontier of discovery. Every experiment, every observation, brings us a little closer to understanding this hidden scaffolding of the universe. Perhaps one day we will finally uncover its nature and see, for the first time, the invisible architecture that holds the stars together. Until then, the galactic halo remains a realm of mystery, vast, dark, and essential. It is the unseen heart of the Milky Way's strength, the quiet companion to all its brilliance, reminding us that sometimes the most important forces in the universe are those we cannot see. As we move through the shadowed vastness of the Milky Way's halo, amid the dark matter that invisibly binds the galaxy together, we encounter some of its oldest and most precious inhabitants, the globular clusters. These ancient, spherical gatherings of stars are like cosmic time capsules, relics of a bygone era that hold within them the secrets of the Milky Way's earliest days. Floating silently in the galactic halo, far above and below the glowing disk, they are reminders of the galaxy's youth, the first great structures to form when the universe itself was still young. A globular cluster is a densely packed sphere containing anywhere from tens of thousands to several million stars, all bound tightly together by gravity. Unlike the loose, irregular open clusters found in the spiral arms, globular clusters are incredibly stable, their stars orbiting in intricate gravitational harmony. They can span 50 to 300 light-years across, and at their cores, the density of stars is staggering, so high that in some regions they appear almost to touch. Yet despite this crowded existence, these stars have coexisted for billions of years, their orbits intertwined in a delicate, ancient ballet. The Milky Way hosts about 150 known globular clusters, though astronomers suspect there may be many more lurking unseen in the distant halo. Some of the most famous include Omega Centauri, M13 in Hercules, and 47 Tucanae, each a glittering swarm of ancient suns. Omega Centauri alone contains over 10 million stars and may, in fact, be the remnant core of a dwarf galaxy long ago absorbed by the Milky Way, a clue to the galaxy's violent and cannibalistic past. These clusters are not just beautiful, they are historical records written in starlight. The stars within them are among the oldest in the galaxy, often over 12 billion years old, nearly as old as the universe itself. They are metal poor, meaning they contain very little of the heavier elements like carbon, oxygen, and iron that younger stars possess. This tells astronomers that globular clusters formed at a time when the universe was still in its early chemical infancy, before successive generations of stars had enriched the cosmos with heavy elements. In studying their composition, scientists gain insight into the conditions that prevailed when the first galaxies began to take shape. The orbits of globular clusters also reveal important clues about the formation of the Milky Way. Many of them move along long, looping trajectories that carry them far beyond the galactic disk and deep into the halo. Some even follow retrograde orbits, moving opposite the galaxy's rotation, suggesting that they may have originated in smaller galaxies that were later captured and assimilated by the Milky Way's gravity. Each cluster, therefore, is a fragment of galactic archaeology, preserving evidence of ancient mergers, collisions, and cosmic migrations that built the Milky Way into what it is today. Globular clusters are also remarkable laboratories for the study of stellar evolution. Because their stars formed around the same time and from the same material, they allow astronomers to test theories of how stars age, how they interact, and how they die. Many clusters contain fascinating stellar remnants, white dwarfs, neutron stars, and even millisecond pulsars, each contributing to the intricate web of stellar life and death that defines these environments. Some clusters harbor exotic objects such as blue stragglers, stars that appear younger and hotter than the rest, possibly formed through stellar mergers or the transfer of mass between binary companions. These unique stars are living proof that even in ancient systems, the drama of creation and destruction continues. Viewed through a telescope, a globular cluster is a breathtaking sight, a dense glowing sphere of countless points of light, like a diamond suspended in darkness. To look upon one is to gaze into the deep past, seeing the same stars that shone when the Milky Way was still forming. They remind us that while much of the galaxy is dynamic and ever-changing, there are still places of enduring stability, where time seems to stand still amid the quiet hum of ancient orbits. In a broader sense, globular clusters connect us to the very origins of structure in the universe. Formed in the aftermath of the Big Bang, they may be among the first building blocks from which galaxies assembled. Some theories suggest that they formed in the dense, early cores of collapsing dark matter halos, later coalescing into the massive galaxies we see today. If that is true, then each globular cluster is a fossil, a surviving piece of the primordial scaffolding of the cosmos. The Milky Way's halo, then, is not a barren wasteland, but a museum of cosmic antiquity, where globular clusters hang like ornaments in the void. Each one is a glowing relic of a time when the universe was still finding its shape, when the first stars were kindled and the first galaxies began to spin. They are the quiet witnesses to our galaxy's birth and growth, guardians of memories written in light that has traveled across eons to reach us. In their silence and endurance, globular clusters embody the timelessness of the Milky Way, proof that even in a universe defined by change and decay, there are structures that persist, carrying the whispers of the beginning through the long night of cosmic history. As we drift back toward the shining plane of the Milky Way, leaving the quiet stillness of the halo behind, we return to the galaxy's beating heart, the galactic disk. This immense, flat structure is where the majority of the Milky Way's visible stars reside, a vast ocean of starlight, dust, and gas that defines the galaxy's iconic spiral shape. But this disk, though seemingly uniform from afar, is not a single continuous layer. It is divided into two distinct components, the thin disk and the thick disk, each with its own unique population of stars, history, and role in the galaxy's evolution. Together, they form the luminous stage upon which most of the Milky Way's story unfolds. The thin disk is the region most familiar to us because it's where the solar system, and nearly all of the galaxy's current star formation, resides. It stretches roughly 100,000 light-years across, but is only about 1,000 light-years thick, making it an incredibly slender structure compared to its width. This thin disk is a dynamic, bustling zone filled with young, bright stars, glowing nebulae, and swirling clouds of interstellar gas and dust. It's here that the galaxy continues to renew itself, forming new generations of stars in dense molecular clouds that trace the spiral arms. The thin disk is rich in what astronomers call metals, elements heavier than hydrogen and helium, because it is constantly replenished by the material recycled from earlier generations of stars. Supernovae and stellar winds continuously enrich the interstellar medium with these heavier elements, which are crucial for the formation of planets and complex chemistry. As a result, the stars here, including our Sun, are metal-rich and relatively young, often less than 8 billion years old. These are the shining blue and white stars that illuminate the spiral arms, the bright nurseries of the Milky Way's ongoing creation. Above and below the thin disk, however, lies a more ancient and enigmatic structure, the thick disk. It is about 3,000 to 4,000 light-years thick, several times thicker than the thin disk, but much dimmer, containing fewer stars and almost no gas. The stars that inhabit this region are older, redder, and more metal-poor, meaning they formed early in the galaxy's history before heavy elements became abundant. These stars are typically 8 to 12 billion years old, remnants of an earlier era when the Milky Way was still taking shape through mergers and turbulent gravitational interactions. The thick disk represents a kind of fossil layer of the galaxy, a relic of its youth. Astronomers believe it may have formed during a chaotic epoch when the Milky Way collided with or absorbed smaller galaxies. These violent interactions could have stirred up the early galactic disk, puffing it up into a thicker structure and scattering its stars into higher orbits above and below the plane. Alternatively, the thick disk may have been the galaxy's first major component, with the thin disk forming later as gas settled into a calmer, flatter configuration. Whatever its origin, it serves as a living archive of the Milky Way's ancient past. The differences between the two disks are not just structural, but also chemical and dynamical. Stars in the thin disk orbit the galactic center in orderly, nearly circular paths, staying close to the plane. In contrast, stars in the thick disk follow more eccentric or inclined orbits, taking them far above and below the galactic plane as they travel. Their lower metallicity reflects the early, less chemically enriched state of the galaxy, offering crucial clues to how the Milky Way evolved over billions of years. What's particularly fascinating is how these two layers interact. Though distinct, they are not entirely separate. Rather, they overlap, blending gradually into one another. Over time, as the thin disk continues to form new stars and the thick disk's population ages further, the boundary between them blurs, showing that the Milky Way is a continuously evolving system, not a static one. Even now, the motions of stars in the disk are subtly reshaped by gravitational influences from the spiral arms, giant molecular clouds, and passing satellite galaxies. For our Sun, nestled comfortably in the thin disk's Orion Arm, this dual-layered structure means that we live in a relatively calm, star-rich neighborhood. Yet, as we look above and below the plane, we are reminded that our galactic home is built on deep foundations, ancient layers of stars that tell the story of how the Milky Way grew from chaos into order. If we could see the galaxy from the side, the thin disk would appear as a narrow, glowing line of light, while the thick disk would form a faint, diffuse halo of reddish stars extending above and below it. It is a vision of structure and age, the youthful brilliance of the thin disk resting atop the quiet endurance of the thick one. Together, they form a bridge across time, from the galaxy's turbulent beginnings to its vibrant, star-filled present. The thick and thin disks are not merely two regions of the Milky Way. They are two chapters of its story, each representing a different era in its cosmic evolution. The thick disk speaks of the galaxy's early struggles, of collisions, formation, and survival, while the thin disk sings of its maturity, of steady creation and stability. In their coexistence, we see the dual nature of the Milky Way itself, a galaxy forever balancing youth and age, chaos and harmony, destruction and rebirth. When we lift our gaze beyond the Milky Way and look outward into the cosmic expanse, our galaxy, immense and intricate as it is, becomes just one among countless others scattered across the observable universe. Each galaxy has its own story, its own structure, and its own unique beauty. Yet by comparing them, we begin to understand our own home more clearly. In this grand cosmic community, the Milky Way stands as a large, mature spiral galaxy, but it is far from the only one of its kind. Neighboring galaxies such as Andromeda, M31, and the Magellanic Clouds offer vivid contrasts that reveal both the diversity and shared heritage of galaxies in our local universe. In size and structure, the Milky Way is a true giant by galactic standards. With a diameter of roughly 100,000 to 120,000 light-years and a mass approaching 1 trillion solar masses, it belongs to the upper range of spiral galaxies, those majestic cosmic disks adorned with bright arms of stars, gas and dust spiraling around a dense central bulge. Its barred structure, the elongated arrangement of stars at the core, is a feature shared by many spiral galaxies, suggesting that such bars play a key role in the evolution and stability of galactic disks, helping funnel gas toward the center and stimulate new star formation. Yet even the Milky Way is overshadowed by its nearest large neighbor, the Andromeda Galaxy, M31. Located about 2.5 million light-years away, Andromeda is slightly larger and more massive than our own galaxy, spanning nearly 150,000 light-years across. Like the Milky Way, it is a barred spiral, but its spiral arms are broader and more open, giving it a somewhat more graceful appearance when viewed in full. Andromeda contains roughly 1 trillion stars, nearly double the number in the Milky Way, and it radiates more overall brightness, marking it as the dominant member of our local group of galaxies. In many ways, Andromeda is like the Milky Way's mirror image, a cosmic sibling of similar age, composition, and structure. Both galaxies are rich in heavy elements, both have supermassive black holes at their centers, and both are surrounded by extensive halos of dark matter and ancient globular clusters. Yet Andromeda appears to have had a slightly more tumultuous past. Observations reveal signs of multiple galactic mergers, ripples in its stellar halo, and streams of stars, remnants of smaller galaxies that Andromeda consumed. These clues suggest that while both galaxies formed through a series of mergers and accretions, Andromeda may have grown faster and larger, giving it a more massive and complex structure. Orbiting both the Milky Way and Andromeda are smaller, irregular galaxies, their cosmic companions. For our galaxy, the two most famous of these are the Large Magellanic Cloud, LMC, and the Small Magellanic Cloud, SMC, visible from the southern hemisphere as faint, cloudy patches in the night sky. These dwarf irregular galaxies, located roughly 160,000 and 200,000 light-years away respectively, are rich in gas and dust, and they serve as vibrant laboratories of star formation. The LMC in particular contains the spectacular Tarantula Nebula, one of the most active star-forming regions known in the local group. The Magellanic Clouds are not merely bystanders, they are in an intricate gravitational dance with the Milky Way. Tidal interactions between our galaxy and these smaller companions have drawn long streams of gas, such as the Magellanic Stream, that stretch across the sky, feeding material into the Milky Way's outer halo. These interactions are a glimpse of how galaxies grow and evolve through mergers and accretion. Over time, the Magellanic Clouds may eventually be absorbed completely into the Milky Way, adding their stars and gas to our galaxy's mass and perhaps triggering new waves of star formation. Beyond Andromeda and the Magellanic Clouds, the local group contains dozens of dwarf spheroidal galaxies, many of which orbit our galaxy or Andromeda as faint, ghostly companions. These tiny galaxies, such as Sagittarius dwarf and Fornax dwarf, are relics of the early universe, often stripped of their gas by gravitational encounters. Their stars are ancient and metal-poor, offering clues to the earliest stages of galaxy formation. In contrast, galaxies like Triangulum, M33, the third largest member of the local group, represent a middle ground, a small spiral galaxy about 60,000 light-years wide, with active star formation and a well-defined disk. When we compare the Milky Way to this galactic family, a picture of cosmic diversity emerges. Galaxies come in many forms: spiral, elliptical, lenticular, and irregular, each shaped by their environment, history, and gravitational interactions. While the Milky Way and Andromeda are grand spirals, galaxies like the Sombrero Galaxy, M104, show off massive central bulges, while others, like Messier 82, blaze with intense starburst activity. Some, like elliptical galaxies, are smooth and ancient, with little gas or dust left to form new stars. The Milky Way sits somewhere in between, mature and balanced, neither too quiet nor too chaotic. In composition too, our galaxy is typical of large spirals, containing roughly 90% dark matter, 9% gas and dust, and only about 1% in the form of visible stars. What makes it extraordinary, however, is that it has reached a stable equilibrium, maintaining its spiral arms and active star formation for billions of years. It is neither a youthful galaxy, still in the throes of creation, nor an aged elliptical fading into stillness. Instead, it stands in the cosmic Middle Age, thriving, balanced, and still evolving. Through these comparisons, we see that the Milky Way is both unique and ordinary, one galaxy among billions, yet singular in its role as our home. Its structure mirrors that of many spirals across the universe. Its past echoes the story of countless cosmic mergers, and its fate, to eventually merge with Andromeda, is part of a universal cycle of transformation. In the grand hierarchy of the cosmos, the Milky Way is neither the largest nor the most luminous, but it is a masterpiece of balance, a galaxy rich in diversity, structure, and life-sustaining chemistry. It is our vantage point in the universe, a shining island of light adrift in the endless dark. And by studying others like it, we begin to understand not only where we live, but also how galaxies live, grow, and change across the infinite sea of time. Beyond the magnificent spiral arms of the Milky Way, where our galaxy's starlight fades into the cosmic dark, lies a broader neighborhood, a grand community of galaxies bound together by the invisible threads of gravity. This region is known as the local group, a vast gravitational family of more than 80 galaxies that drift and evolve together in the quiet depths of intergalactic space. The local group is our galactic ecosystem, the small patch of the universe we call home, and understanding it gives us insight into how galaxies grow, interact, and eventually merge to shape the large-scale structure of the cosmos. At the heart of the local group are its two colossal members, the Milky Way and the Andromeda Galaxy, M31. Together, they dominate the group's mass and structure, accounting for nearly all of its gravitational influence. The Milky Way and Andromeda are like twin giants orbiting a shared center of mass, gradually pulling toward each other in a slow, inevitable dance that will culminate in a cosmic merger billions of years from now. The third largest member, the Triangulum Galaxy, M33, is a smaller spiral system that likely orbits Andromeda and may one day become part of their future union. Surrounding these great spirals is a retinue of dwarf galaxies, each unique in shape, size, and history. The Milky Way alone is orbited by more than 50 known satellite galaxies, ranging from relatively large systems like the Large and Small Magellanic Clouds to much fainter and older dwarf spheroidals such as Draco, Sculptor, and Sagittarius Dwarf. These diminutive galaxies are the fossils of galactic formation, relics from the early universe that survived the violent mergers and collisions that built the larger galaxies we see today. Many of them are slowly being torn apart by the Milky Way's gravity, leaving behind tidal streams of stars that arc across the sky, their luminous trails marking the ongoing process of galactic evolution. The local group spans about 10 million light-years across, though most of its mass is concentrated within a few million light-years of its core, where the Milky Way and Andromeda reside. Between these two giants lies a vast region of space filled with a tenuous web of gas, dust, and dark matter, an intergalactic medium so thin that it would seem empty even to the most sensitive instruments, yet it quietly binds the entire group together. Within this space, galaxies drift slowly under mutual gravitational attraction, interacting over timescales that stretch across billions of years. While the Milky Way and Andromeda are the local group's dominant forces, the smaller galaxies play essential roles in its evolution. Their gravitational interactions can trigger bursts of star formation, reshape spiral arms, and even alter the trajectories of larger galaxies. These minor galaxies act like cosmic catalysts, nudging, merging, and enriching the group's structure. Many of them are believed to be remnants of ancient mergers or fragments of larger systems that were stripped apart over time. The Sagittarius dwarf galaxy, for example, is currently being absorbed by the Milky Way, its stars stretched into a glowing river that wraps around our galaxy like a celestial ribbon. Interestingly, the local group is not isolated. It is part of an even greater assembly known as the local sheet, a flattened region of space where galaxies share a similar velocity and motion through the cosmos. Beyond that lies the local supercluster called Laniakea, an immense network of tens of thousands of galaxies spanning over 500 million light-years. Within this cosmic web, gravity weaves everything together, connecting clusters and groups into the vast tapestry of the universe. The local group is but one small node in this enormous structure, a single drop in an ocean of galactic collectives. Yet despite its modest scale, the local group is a microcosm of galactic evolution. Here, we witness every stage of the galactic life cycle: new star formation in the Magellanic Clouds, quiet old age in dwarf ellipticals, and the grand approach of two spirals destined to merge. These interactions are slow and subtle, unfolding not in years or centuries, but over hundreds of millions of years. Yet they shape the galaxies profoundly. Over time, the local group's members will continue to merge and evolve, gradually consolidating into a single, massive elliptical galaxy surrounded by a faint halo of remnants. The gravitational relationships between the Milky Way, Andromeda, and their smaller companions also remind us that galaxies are not isolated islands, but deeply interconnected systems. Just as stars within a galaxy interact through gravity, so too do galaxies within a group. These connections are the scaffolding of the universe's architecture, from the smallest star cluster to the largest cosmic filament. And yet, even within this immense galactic neighborhood, our own vantage point is humbling. When viewed from Andromeda or Triangulum, the Milky Way would appear as a majestic spiral, glowing softly in the dark. One galaxy among many, bound together in a cosmic ballet that began billions of years ago and continues to this day. The local group is, in essence, the Milky Way's cosmic family, its gravitational tribe amid the vast cosmic wilderness. It is both a snapshot of the universe's dynamic past and a preview of its distant future. Within it, galaxies collide, merge, and transform, teaching us that the universe is not static, but alive with movement. A grand, interconnected system where everything, from the smallest star to the largest supercluster, is part of the same eternal flow. As we survey the great celestial neighborhood of the local group, the grandest and most inevitable event looming in the Milky Way's future comes into focus: the cosmic collision between our galaxy and the Andromeda Galaxy M31. It is a slow-motion dance of unimaginable scale, a gravitational rendezvous that has been unfolding for billions of years and will culminate in a breathtaking transformation roughly 4 billion years from now. Though the thought of galaxies colliding might conjure images of cataclysm and chaos, the reality is far more graceful. A silent cosmic waltz that will reshape both galaxies and give birth to an entirely new one. The Andromeda Galaxy lies about 2.5 million light-years away, yet its approach toward us is steady and unstoppable. Astronomers have measured that Andromeda is moving in our direction at a speed of about 110 kilometers per second, roughly 250,000 miles per hour. Though the vast emptiness of intergalactic space separates us now, the two galaxies are bound by gravity, locked in an inevitable trajectory toward one another. Over the next few billion years, they will continue to close the distance until their halos, the vast, invisible spheres of dark matter and hot gas surrounding each galaxy, begin to overlap. When this happens, the skies of any surviving civilizations in the far future will transform into a spectacle beyond imagination. Andromeda, which today appears as a faint smudge of light in the constellation of the same name, will grow larger and brighter with each passing eon. Hundreds of millions of years before the final merger, it will dominate the night sky, a swirling, luminous spiral larger than the moon, its vast arms stretching across the heavens. Eventually, as the galaxies draw close enough, tidal forces will begin to distort their shapes. Their elegant spiral structures will twist and warp as stars, gas, and dust are drawn out into long flowing tidal streams, forming arcs of light that will span tens of thousands of light-years. Contrary to what one might imagine, this galactic collision will not involve stars smashing into one another. The distances between stars are so immense that even as two galaxies interpenetrate, the odds of any two stars actually colliding are minuscule. Instead, what will truly merge are their gravitational fields and interstellar materials. As the galaxies intertwine, their gas clouds will collide and compress, triggering spectacular waves of star formation, entire generations of new stars bursting into life amid the chaos. The night sky, once serene, will become a living canvas of light, color, and movement. Over the course of several close passes spanning hundreds of millions of years, the Milky Way and Andromeda will gradually lose their distinct shapes. Their spiral arms will stretch, fold, and dissolve, and their central regions will merge into one enormous core. Eventually, the two galaxies will settle into a single, massive elliptical galaxy, which astronomers have already given a name: Milkomeda, or sometimes Milkdromeda, a cosmic fusion of the Milky Way and Andromeda. This new galaxy will likely span more than 300,000 light-years across, its stars orbiting in a vast spheroidal cloud rather than the thin, orderly disk that characterizes our current spiral form. At the very center of this merged galaxy, an even more extraordinary event will unfold: the union of two supermassive black holes. The Milky Way's Sagittarius A, with its mass of about 4 million suns, and Andromeda's central black hole, which is about 100 million solar masses, will slowly spiral toward each other. As they draw closer, they will release enormous amounts of gravitational radiation, ripples in space-time that will echo across the universe. When they finally merge, they will form a single, even more powerful black hole, the new heart of Milkomeda, surrounded by swarms of stars moving in intricate, elliptical orbits. Despite the grandeur of this event, the solar system itself may not be directly destroyed, though its fate is uncertain. Simulations suggest that as the galaxies merge, gravitational interactions could fling the Sun and its planets into a new orbit, possibly farther from the galactic center or even into intergalactic space. By that time, however, the Sun will have already entered its red giant phase, having exhausted much of its hydrogen fuel, so any life that may have once existed on Earth will likely be long gone. Humanity, if it still exists, will be witnessing the event from another world, or perhaps from beyond the confines of the Milky Way entirely. From a cosmic perspective, this galactic merger is far from unique. Across the universe, galaxies are constantly colliding and coalescing, driven together by gravity's irresistible pull. Indeed, this process is one of the fundamental mechanisms by which galaxies grow and evolve. The Milky Way itself is a product of countless earlier mergers, smaller galaxies that were swallowed and absorbed over billions of years, their stars and gas becoming part of our own. The future collision with Andromeda is simply the next step in that long evolutionary journey. When the dust finally settles, Milky will shine as a giant elliptical galaxy, its star formation slowing over time as it consumes its remaining gas. The spiral patterns of both parent galaxies will be gone, replaced by a smooth, glowing halo of billions of stars, ancient survivors of two once separate worlds. Over the following billions of years, the merged galaxy will gradually grow quieter, its young blue stars dying off, leaving behind a calm sea of red and yellow suns. The story of the Milky Way and Andromeda's merger is not one of destruction, but of transformation, a cosmic renewal on the grandest scale. It is a reminder that in the universe, nothing stands still, and even the most enduring structures are part of a vast cycle of change. Just as stars live, die, and are reborn, so too do galaxies evolve through collisions and unions, each merger giving rise to new forms of beauty and complexity. One day, billions of years from now, long after humanity's brief spark has faded, our galaxy will no longer exist as we know it. Yet the starlight of the Milky Way, its essence, its atoms, its legacy, will live on within a greater whole, shining forever as part of a new, majestic galaxy born from the union of two giants. As the Milky Way spins onward through cosmic time, its vast arms and endless stars remind us of an inescapable question. Are we alone in this galaxy of worlds? The more we learn about our galactic home, the more we realize that planets are not rare exceptions, but common companions to stars. Across the Milky Way, there may be hundreds of billions of planets, each with its own environment, chemistry, and story. Among them, countless worlds may host conditions suitable for life, and the search for these exoplanets and for potential habitability has become one of humanity's most profound scientific pursuits. For centuries, Earth was the only known world with oceans, clouds, and life. That changed dramatically in 1992, when astronomers made the first confirmed discovery of planets beyond our solar system. Two small worlds orbiting a pulsar, a rapidly rotating neutron star. 3 years later, in 1995, a new milestone arrived: the detection of 51 Pegasi b, the first planet found around a sun-like star. This gas giant, orbiting perilously close to its host, defied our expectations of how planetary systems should look. Since then, with the help of ground-based telescopes and space observatories like Kepler, TESS, and James Webb, astronomers have discovered more than 5,000 confirmed exoplanets, with thousands more candidates awaiting verification. These discoveries have revolutionized our understanding of planetary diversity. We've found worlds that baffle the imagination, hot Jupiters that orbit their stars in days, super-Earths with double Earth's mass, and mini-Neptunes cloaked in thick atmospheres. There are planets where molten rock rains from iron clouds, worlds locked in eternal daylight on one side and endless night on the other, and frozen giants adrift in the cold, lonely darkness between the stars. The Milky Way is a gallery of the extraordinary, proof that nature's creativity knows no bounds. Yet, amid all this variety, the search for habitable worlds continues to guide our exploration. Astronomers define the habitable zone as the region around a star where temperatures allow liquid water to exist on a planet's surface, neither too hot nor too cold. Within this delicate band, the conditions for life as we know it could arise. But habitability is far more complex than just temperature. It depends on atmosphere, magnetic field, geology, and even the stability of a planet's orbit. Among the thousands of discovered worlds, several stand out as promising candidates. Planets like Kepler 452b, TO1 700d, and LHS 1140b orbit within their stars' habitable zones and have sizes similar to Earth's. Others, like TRAPPIST-1's 7 planets, form compact systems around a small red dwarf star, with several worlds that may host liquid water. Some of these exoplanets lie only a few dozen light-years away, close enough that future telescopes might analyze their atmospheres for signs of oxygen, methane, or other biosignatures that could hint at life. The sheer number of planets discovered has changed the way we think about the Milky Way. Statistically, nearly every star likely hosts at least one planet, and many may have entire families of them. With more than 200 billion stars in the galaxy, there could easily be 100 billion or more planets, and perhaps billions of Earth-like worlds. The possibility that life might have arisen elsewhere, under alien suns, is no longer the realm of imagination, but a legitimate scientific hypothesis awaiting evidence. This search drives much of our modern astronomical exploration. The Kepler Space Telescope first revealed the incredible prevalence of planets, while its successor, TESS Transiting Exoplanet Survey Satellite, continues to identify nearby candidates for detailed study. Meanwhile, the James Webb Space Telescope is now peering into the atmospheres of distant exoplanets, analyzing their light for chemical fingerprints that could indicate habitability or even biology. Ground-based observatories, too, are pushing forward, with new technologies allowing us to directly image exoplanets, faint dots of reflected light beside the overwhelming glare of their stars. But the search for habitability is not just scientific, it is deeply philosophical. It forces us to look inward as much as outward. Each exoplanet we discover expands our understanding of what home can mean. Perhaps there are worlds with purple skies and methane seas, or planets orbiting twin suns, their horizons aglow with perpetual dawn. Perhaps some harbor oceans beneath icy crusts, warmed by internal heat, where alien life thrives in darkness, as it does around Earth's deep-sea vents. The idea that we might not be alone transforms the Milky Way from a backdrop of distant stars into a living, dynamic ecosystem, a galaxy filled with potential homes and life forms waiting to be found. It connects us to the cosmic story not as passive observers, but as participants in a shared galactic heritage. And yet, even as our instruments grow more powerful and our discoveries more frequent, we are still at the very beginning of this journey. The nearest potentially habitable exoplanet, Proxima Centauri b, orbits the star closest to our own, just 4.2 light-years away. But even that small distance is unimaginably vast. Our fastest spacecraft would take tens of thousands of years to reach it. The technological and philosophical challenges of exploring these distant worlds remind us that the search for life is not only about finding new planets, but also about understanding our place in the galactic whole. In the end, the discovery of exoplanets has turned the Milky Way into a galaxy of possibility. Each new world is a promise, each discovery a reminder that the universe is not static or barren, but vibrant and full of potential. Whether we find life elsewhere or not, the pursuit itself is a testament to the curiosity and resilience of our species. The first known beings to look across the gulf of space and ask, Who else might be out there? When we step back to truly consider the scale of the Milky Way, even the most vivid imagination strains to grasp its immensity. Our galaxy, a luminous spiral stretching over 100,000 light-years across, is so vast that the numbers describing it lose their meaning when compared to the human experience. Each pinpoint of light we see in the night sky, each star, each glowing nebula, represents only a minuscule fragment of the galactic whole. Between those distant suns lie enormous gulfs of emptiness, regions so wide and silent that light itself, the fastest thing in the universe, takes years, even millennia, to traverse them. To understand the scale, let us start close to home. The Sun is about 150 million kilometers, 93 million miles, from Earth, a distance we call 1 astronomical unit, AU. It takes light just over 8 minutes to travel from the Sun to us. Yet the nearest star system, Alpha Centauri, lies 4.37 light-years away. That's nearly 40 trillion kilometers. At that distance, even the fastest spacecraft ever built, Voyager 1, launched in 1977 and now speeding through interstellar space, would need more than 75,000 years to reach it. In human terms, that's longer than the entire span of recorded history. Now imagine crossing the entire Milky Way, even traveling at the speed of light, an impossible feat for any human-made craft. It would take over 100,000 years to journey from one side of the galaxy to the other. For perspective, if the Milky Way were shrunk down to the size of North America, our solar system would be no larger than a coin, and Earth itself smaller than a grain of dust within that coin. The gulf between stars is not measured in kilometers or miles, but in light years, a unit born of necessity because no smaller measure can adequately express such immensity. Our spacecraft, the Voyagers, Pioneers, and New Horizons, are now drifting beyond the outer limits of the solar system, silent emissaries of human curiosity. Yet even after decades of travel, they have barely stepped off the cosmic shoreline. The nearest interstellar destination remains unimaginably far beyond their reach. If we scaled down the Milky Way to the size of a football field, Voyager 1 would not yet have crossed the thickness of a single human hair. And yet, this immense scale is also what gives the galaxy its wonder. Every one of those distant suns we see is a potential home for planets, moons, and perhaps life. The Milky Way contains hundreds of billions of stars, and between those stars, trillions of worlds orbit quietly through time. Though they are separated by vast distances, the galaxy itself is bound together by gravity, a delicate web that unites everything from the smallest dust grain to the greatest star cluster. The sheer magnitude of these distances also changes how we perceive time. When we look at distant stars or nebulae, we are not seeing them as they are now, but as they were thousands or even tens of thousands of years ago, because their light has taken that long to reach us. To gaze into the night sky is to look into the past, to witness ancient starlight that began its journey long before humanity learned to speak, build, or dream. The galaxy is a time machine as much as it is a place. Even our understanding of movement becomes distorted at this scale. The Sun, for instance, is not fixed in space, but races around the center of the Milky Way at 230 kilometers per second, 514,000 miles per hour, completing one galactic orbit every 230 million years. Our entire solar system, with its planets, comets, and drifting asteroids, rides this invisible current through space, tracing a path that has carried it through 20 galactic years since the Sun's birth. In that time, the galaxy itself has changed. Stars have been born and died. Spiral arms have shifted, and other galaxies have drawn closer. To comprehend the Milky Way's scale is to confront a truth that is both humbling and awe-inspiring. We are impossibly small. All of human civilization, every empire, discovery and dream, has unfolded within a mere blink of galactic time, confined to a single fragile world, orbiting a single ordinary star. And yet, that same smallness carries profound meaning. It reminds us that our search for understanding, our effort to measure, map, and imagine the galaxy, is itself an act of cosmic significance. Against all odds, a species that evolved on a dust mote of a planet has come to understand the vast structure of the galaxy that gave it life. Our place in the Milky Way is that of both participant and observer, a spark of consciousness adrift in a sea of stars, capable of comprehending distances so vast that even light grows weary crossing them. Every photon that reaches our eyes carries with it a story from across the eons, a whisper from the galaxy's ancient heart. And while we may never, with our current technology, cross the Milky Way's full breadth, the very act of imagining it, of knowing where we stand within it, expands the boundaries of our awareness. The galaxy's vastness is not a barrier, but an invitation to explore, to learn, and to dream. For though the distances between the stars are immense, the human spirit, driven by curiosity and wonder, reaches farther still. From our small perch on the edge of a spiral arm, humanity has gazed into the Milky Way with a longing as old as consciousness itself. For millennia, we saw it only as a misty ribbon of light stretching across the night sky, a celestial river, a road of spirits, or a pathway to the divine. Ancient civilizations could not have known that this shimmering band was composed of billions of distant stars, each a sun like our own, woven into the grand spiral of our galaxy. Yet today, through the power of observation, technology, and imagination, we have begun to unravel its true nature. Human exploration and observation of the Milky Way stand among the greatest intellectual achievements of our species, a testament to our ability to see beyond our immediate world and understand the vast cosmic structure that cradles us. Our journey toward understanding began with the unaided eye. Early astronomers like the Babylonians, Mayans, and Greeks carefully charted the stars and constellations, embedding them into myth and navigation. But it was Galileo Galilei, in 1610, who first pointed a telescope toward the Milky Way and made a revolutionary discovery: that the milky glow was not a continuous mist, but a dense field of stars. His simple refracting telescope opened humanity's eyes to the galaxy's true nature and laid the foundation for centuries of exploration that followed. As telescopes grew more powerful, astronomers began to map the Milky Way in greater detail. In the late 18th century, William and Caroline Herschel made one of the first attempts to chart its shape. By counting stars in different directions, they concluded that the Sun lay roughly in the center of a flattened, disc-like system. A pioneering effort, though limited by the haze of interstellar dust that obscured much of the galaxy from view. It wasn't until the 20th century, through the work of Harlow Shapley, that our true place in the cosmos was revealed. By studying globular clusters, Shapley determined that they formed a roughly spherical halo around the Milky Way, and that the center of this distribution lay far away in the direction of Sagittarius. Humanity had been dethroned from the center of the galaxy, much as it had once been displaced from the center of the solar system by Copernicus. But even with optical telescopes, much of the Milky Way remained hidden. Dust and gas in the galactic plain block, visible light, rendering vast regions opaque to our eyes. The breakthrough came in the mid-20th century with the advent of radio astronomy, which allowed us to see through this cosmic fog. In 1951, astronomers Harold Ewan and Edward Purcell detected the faint radio emission from neutral hydrogen, the 21-centimeter line, a signal emitted by interstellar hydrogen atoms as they flip their spins. This discovery transformed galactic astronomy. By mapping the 21-centimeter radio emission across the sky, scientists were able to trace the structure of the Milky Way's spiral arms and measure its rotation curve, revealing the vast disk in which we reside. Radio telescopes, such as the Arecibo Observatory, Parkes Radio Telescope, and later arrays like the Very Large Array, VLA, and ALMA, Atacama Large, millimeter/submillimeter array, have since given us an extraordinary view of the galaxy in wavelengths invisible to the human eye. They have revealed the dense molecular clouds where stars are born, the supernova remnants left by dying stars, and the filaments of gas connecting regions across thousands of light years. Through these instruments, astronomers have traced the invisible skeleton of the Milky Way, mapping both its visible and hidden components. The exploration of our galaxy took another leap forward when we left Earth's atmosphere. The launch of space telescopes allowed us to observe the Milky Way across the full spectrum of light, from infrared to X-rays, free from the distortions and absorption of our atmosphere. The Infrared Astronomical Satellite, IRAS, and later missions like Spitzer and WISE opened up the dusty heart of the Milky Way, where newborn stars and nebulae glow faintly in heat. These infrared observatories allowed astronomers to peer straight into regions that visible light cannot penetrate, revealing the galactic center and the swirling chaos around Sagittarius A, our galaxy's supermassive black hole. Meanwhile, X-ray observatories such as Chandra and XMM Newton have shown us the high-energy universe, the violent aftermaths of supernovae, the hot gas streaming through the galactic halo, and the fierce radiation emitted by neutron stars and black holes. Gamma-ray telescopes have detected the faint but persistent glow of radioactive isotopes, evidence of the ongoing cycle of star birth and death across the Milky Way. Each wavelength tells a different part of the story, and together they form a complete picture of a living, breathing galaxy. Perhaps the most transformative tool of all, however, has been the Gaia Space Observatory, launched by the European Space Agency in 2013. Gaia has created the most precise 3D map of the Milky Way ever made, measuring the positions, distances, and motions of more than 1.8 billion stars. By tracking how stars move, Gaia allows astronomers to reconstruct the Milky Way's dynamic history, how it formed, how it grew through mergers, and how it continues to evolve. Gaia's data has even revealed the ghostly remains of ancient galaxies absorbed by the Milky Way, their stars now scattered throughout the halo. One such discovery, the Gaia Enceladus Sausage Galaxy, tells of a colossal merger that occurred about 10 billion years ago, a defining moment in our galaxy's early growth. Humanity's ability to explore the Milky Way has also extended into the realm of direct exploration, however limited it may still be. Our spacecraft, Voyager 1 and 2, Pioneer 10 and 11, and New Horizons, have ventured beyond the boundaries of the solar system, carrying with them not only scientific instruments, but also messages from Earth, engraved on plaques and golden records. These artifacts serve as symbolic ambassadors, reminders that even the smallest beings on a small planet can aspire to touch the infinite. Though they move at extraordinary speeds by human standards, they have yet to travel even one light day from home, proof of how immense the Milky Way truly is. On Earth, new generations of telescopes are continuing to revolutionize our understanding. The Vera C. Rubin Observatory, with its vast mirror and wide field of view, is designed to capture the ever-changing night sky, detecting billions of new stars, variables, and transient events. The Square Kilometre Array, SKA, now under construction, will be the largest radio telescope ever built, mapping the galaxy's hydrogen in unprecedented detail. Meanwhile, the James Webb Space Telescope, JWST, with its unparalleled sensitivity in the infrared, is already unveiling the earliest stages of star and planet formation within the Milky Way's dusty nurseries. All these instruments, working together across the electromagnetic spectrum, are turning the Milky Way from a mystery into a map. Yet, for all our progress, much remains hidden. Only about 10% of our galaxy's stars have been observed directly. The rest are veiled by dust, distance, or faintness. The dark matter halo, though its gravitational effects are well documented, remains invisible. And even as we chart the spiral arms and measure the galaxy's rotation, we continue to uncover surprises, new structures like the Radcliffe Wave, a vast undulating chain of star-forming regions that reshaped our understanding of the galactic disk. Still, the story of how we study the Milky Way is ultimately a story of perspective and perseverance. We are confined to a single vantage point within one spiral arm, yet from this limited position, we have mapped a galaxy 100,000 light-years wide. Using only light and mathematics, we have deduced the presence of dark matter, traced the history of star formation, and peered into the hidden heart of our galactic core. We have done all this from a tiny blue planet orbiting an ordinary star, using instruments built by hands that only recently learned to reach beyond the sky. Our understanding of the Milky Way continues to deepen with every new mission and telescope. And as we push further into the unknown, exploring with radio waves, photons, and gravity itself, we carry with us the same spirit that first drove Galileo to look upward. The desire to know where we are and what we are part of. For in studying the Milky Way, we are not merely observing a galaxy, we are unraveling our cosmic origins, tracing the long interconnected story that began with hydrogen atoms in the early universe and continues through every star, planet, and living being that has ever existed. Through exploration, we are learning that the Milky Way is not just our home, it is our history, our heritage, and our connection to everything that ever was or ever will be. Even with centuries of observation, billions of data points, and the most advanced telescopes humanity has ever built, the Milky Way remains, in many ways, a mystery. For all our maps and models, we have only glimpsed fragments of its true structure, faint outlines of an ocean whose depths we have barely begun to sound. Much of our galaxy remains unexplored, invisible, or entirely unknown, concealed behind curtains of cosmic dust, hidden beyond the reach of even our most sensitive instruments, or existing in forms we do not yet understand. The Milky Way, it seems, guards its secrets well. From our position within one of its spiral arms, we see the galaxy from the inside, a vantage both intimate and limiting. Like travelers lost in a vast forest, we can see the trees nearby in exquisite detail, but the full shape of the forest remains hidden from view. The interstellar dust that drifts through the galactic plane absorbs and scatters visible light, blocking our direct line of sight to enormous regions of the galaxy. This dust, composed of microscopic grains of carbon and silicate, forms a murky veil that obscures the inner spiral arms and even the galactic center, where our supermassive black hole, Sagittarius A, resides. What lies beyond that dusty curtain is still a matter of ongoing discovery. Infrared and radio telescopes have allowed us to peer through the darkness, revealing star clusters, molecular clouds, and the glowing gas of nebulae. But even these powerful tools can only see so far. Beyond the disk lies a vast and sparsely populated galactic halo, extending hundreds of thousands of light-years in every direction. The halo's faint stars and mysterious dark matter make it almost impossible to observe directly. We know it exists. Its gravitational influence keeps the galaxy intact, yet its exact structure, mass, and composition remain shrouded in uncertainty. Somewhere out there may be remnants of long-lost galaxies the Milky Way devoured, their stars now scattered like ghostly embers drifting through the void. Even within the regions we have studied, mysteries persist. The spiral arms themselves, once thought to be simple, continuous structures, now appear to be fragmented, irregular, and rippling, like waves in a galactic sea. Astronomers recently discovered the Radcliffe Wave, a colossal undulating chain of star-forming regions stretching 9,000 light-years long and weaving through our local arm. This vast structure was invisible to us until recently, hidden in plain sight because we lacked the precision to detect its pattern. If such a monumental feature could remain undiscovered so close to home, what else might be concealed in the farthest reaches of the Milky Way? The galactic center, too, holds enigmas that challenge our understanding of physics. Though we have imaged the glowing ring around Sagittarius A using the Event Horizon telescope, the region around it is a turbulent realm of magnetic fields, swirling plasma, and high-energy particles. Strange filaments of radiation crisscross the area, their origin uncertain. Even the exact nature of how our galaxy's supermassive black hole interacts with its surroundings, how it feeds, flares, and influences the birth of nearby stars, remains only partly understood. Beyond the visible and radio spectrum lies the unseen frontier of dark matter, which makes up most of the Milky Way's mass. We cannot observe it directly. We can only infer its existence through its gravitational pull on stars and gas. What this dark matter actually is, particles, fields, or something yet unimagined, stands as one of the greatest unsolved questions in science. It is the unseen scaffolding upon which the entire galaxy is built, yet it is utterly invisible to our eyes and instruments. If we could somehow see it, the Milky Way would appear vastly different, its faint luminous disk suspended within a colossal, ghostly sphere of invisible substance. And then there is the dark baryonic matter, the ordinary matter we can't see even though it's not dark in the exotic sense. The cold gas, rogue planets, black holes, and faint brown dwarfs drifting unlit through the galaxy. Some scientists believe that a significant portion of the Milky Way's true mass is hidden in these dim, undetectable forms. Between the stars may float billions of rogue planets, untethered to any sun, drifting silently through the galactic night. We have only begun to estimate how many might exist, perhaps as many as 10 times the number of stars themselves. These unseen worlds, dark and frozen, are a reminder that even within the known, there is hidden vastness. The mystery extends not just to matter, but to motion and dynamics. The Milky Way's rotation curve, the way its stars orbit the center, does not behave as expected. Even with dark matter accounted for, there are still subtle irregularities we cannot explain. The galaxy's spiral arms appear to rise and fall like waves, hinting that it may be warped or twisted, possibly by the gravitational influence of nearby satellite galaxies, like the Large Magellanic Cloud. The halo, once thought to be spherical, may be stretched or lopsided. Every new observation reveals more complexity, showing that our galaxy is far from the static, orderly spiral once depicted in textbooks. It is alive, dynamic, and still evolving. And perhaps most tantalizing of all, there is the mystery of life. For all the exoplanets we've found, for all the billions of stars that may host them, we have yet to detect a single confirmed sign of life beyond Earth. It is the galaxy's most haunting silence, the so-called Fermi paradox. If life is common in the universe, where is everyone? Are we early arrivals in a still young galaxy, or latecomers in a universe where most civilizations have already flickered out? Could the vast stretches of time and distance simply make communication impossible? Or is life itself a rare and fragile anomaly, existing only here, on one small world, orbiting one modest star? These unanswered questions remind us that, for all our progress, we have only scratched the surface of understanding our galactic home. The Milky Way remains a frontier of discovery, filled with regions uncharted and phenomena unexplained. Even as our telescopes grow sharper and our simulations more sophisticated, the galaxy continues to hold surprises that defy expectation. From newly discovered star streams to hidden stellar populations and mysterious cosmic signals that reach us from the depths of space. Yet, it is precisely this mystery of the unknown that makes our exploration of the Milky Way so profoundly meaningful. The darkness between the stars is not emptiness, but potential, a canvas of unanswered questions waiting to be illuminated. Each new discovery, whether a planet, a nebula, or a gravitational anomaly, is a reminder that the universe is deeper, stranger, and more wondrous than we can imagine. In the end, the unknown is not something to fear, but to revere. It is the source of curiosity, the driving force that compels us to look upward, build telescopes, launch probes, and ask questions we do not yet know how to answer. The Milky Way still hides most of its secrets, but that is what keeps us searching. For as long as the galaxy keeps its mysteries, humanity will keep seeking. Our instruments reaching farther, our minds reaching deeper, and our dreams forever expanding into the darkness that surrounds us. When we finally pause to take in everything we've discovered, from the swirling arms of the Milky Way to the dark halo that holds it together, from the births and deaths of stars to the invisible mysteries still veiled in dust, a single truth emerges with quiet clarity. We are impossibly small, yet deeply connected to it all. Humanity exists as a brief spark of awareness within a galaxy 100,000 light-years wide, one of billions that drift through an expanding universe. And yet, from this tiny corner of one spiral arm, consciousness has arisen, capable not only of observing the cosmos, but of understanding it. Every atom in our bodies was forged in the heart of a star. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was born in ancient stellar furnaces and scattered into space by supernovae long before our sun existed. We are, quite literally, the Milky Way made conscious, the galaxy looking inward upon itself. Through our eyes, it can see its own stars. Through our thoughts, it can ponder its own history. For billions of years, the Milky Way spun in silence. Only recently, on one small world orbiting one average star, it found a voice that could ask, "Where did we come from?" When we look up at the band of the Milky Way stretching across the night sky, what we are truly seeing is our origin and our destiny, a river of starlight connecting the past to the future. Those countless points of light represent generations of suns, each a chapter in the story of creation, death, and renewal. Some of them burned out eons ago. Their light is only reaching us now. Others are still being born, igniting in distant nebulae. In that grand continuum, our entire existence, every civilization, every dream, every heartbeat, occupies but a fleeting instant. And yet, in that instant, we have learned to see the galaxy as it is, vast, dynamic, and alive. It's humbling to know that, even if humanity were to vanish tomorrow, the Milky Way would go on unchanged, its stars continuing to orbit, collide, and evolve for billions of years more. Our presence does not alter the galaxy's course. But what makes our existence remarkable is not our scale, but our awareness. The universe has given rise to a species capable of wonder, capable of feeling awe at the very vastness that diminishes it. That, perhaps, is our cosmic purpose, not to rule, not to last forever, but to bear witness to the immensity from which we came. In a galaxy of silent stars, consciousness is rare. We are the voice of the Milky Way, the fleeting thought in an ancient mind. Our telescopes, our probes, our questions, all are extensions of that singular desire to know. And in that pursuit, we give meaning to the void. Each discovery, each photograph of a nebula, each calculation of a star's orbit is an act of reverence, an acknowledgement that, though we are small, we are part of something magnificent. The Milky Way does not know we exist. It neither notices nor cares. Yet we notice it, and in doing so, we transform the galaxy from a cold expanse of matter into a place of wonder. The night sky is not just a backdrop, it is our ancestry written in light. Every photon that reaches our eyes has traveled across time and space to tell us that we belong to something vast beyond comprehension. And yet, somehow, we are capable of comprehending it. So when you stand beneath the stars and see that pale band of light arching across the heavens, remember what it represents. Billions of suns, countless worlds, and a timeless story of birth and decay, beauty and chaos. And remember too that you are part of that story. You are made of the same elements that shine above you. You are a child of the galaxy, ephemeral, fragile, but aware. The Milky Way's spirals will continue to turn long after we are gone, but the light of understanding we have kindled will remain part of its history forever. In the end, perhaps that is enough. To know that, for one brief moment in cosmic time, the galaxy awakened within us and saw itself, not through starlight, but through the eyes of beings who could wonder. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.